Hello, my name is Steven Stella, and I'm a power management product marketer in our analog division here at Microchip Technology. I'd like to introduce you to our MCP19035 Microchip's analog-based step-down DC-to-DC PWM controller family. Now first, it's important to note that the MCP19035 is a PWM controller, meaning that it drives an external MOSFET. While there's a lot of pressure to integrate the MOSFET switching devices, just given the diverse array of power conversion applications, an external power device allows the power designer to make trade-off decisions that impact the power rating, efficiency, and cost of the total solution. Controllers also support higher power levels than can typically be found in an integrated regulator, up to 100 watts in the case of the MCP19035, and potentially higher in certain applications. The MCP19035 is a conventional voltage mode DC-to-DC controller with integrated logic level MOSFET drivers arranged in a synchronous buck configuration. It operates over a wide input voltage range from 4.5 to 30 volts, enabling it to accept 5, 12, and even up to 24 volt input voltage rails. It's available in either 300 or 600 kilohertz switching frequencies, both orderable by the factory, allowing you to trade off the efficiency of the 300 kilohertz version for the overall reduced footprint size provided by the 600 kilohertz version. The output voltage is adjustable via the standard voltage feedback resistors, and the integrated MOSFET drivers are sized to support loads of up to 20 amps. Overall, the MCP19035 is a very solid and fast analog-based DC-to-DC controller, but that's not enough. We took care to design it to work with the industry's latest low figure of merit MOSFET devices. The figure of merit, or FOM, of MOSFET devices is the on-state resistance in milliohms multiplied by the gate charge in nanocoulombs. These two variables, on-state resistance and gate charge, are representative of the two key loss mechanisms in switching devices. For today's low FOM MOSFETs, you typically see FOMs in the low 30s and even down into the mid-20s. Just a few years ago, low FOM devices could be 90. So you can see that in a short amount of time, a lot of progress has been made on reducing MOSFET FOM and enabling significant efficiency improvements in power conversion applications. For instance, when replacing old MOSFETs with the latest of MOSFET technology, we've seen increases in power conversion efficiency of up to 2%. Now 2% may not sound like a lot, but with power conversion efficiencies in the 90% range, 2% is equivalent to a 20% reduction in losses. The easiest way to think about this is 90% efficient power conversion. That still means there's 10% loss. A 2% improvement, 2 divided by 10, is a 20% reduction in losses. That's a lot. But it's worth noting that if you don't use a controller that's able to take advantage of these new MOSFET technologies, then you're not realizing all of the benefits. So how does a controller matter? Well, it's easiest to refer to one of Microchip's application notes, our AN1471. The key is held in equation 12, specifically the DT, or the MOSFET dead time. This is the time that the high side and low side MOSFETs are both held in the off state between switching to avoid cross conduction, or the condition when both MOSFETs conduct at the same time. You can see in a synchronous buck configuration, when both MOSFETs are conducting, the input voltage is shorted directly to ground. Now that's not desirable. Dead time is added in the drive circuitry to avoid this situation. However, we can see that this time directly impacts the conduction loss in the diode, and this loss is significant. Low FOM MOSFETs with smaller QG turn on and off faster, and thus require less dead time to avoid the cross-conduction situation. By reducing this dead time, we're able to take the disproportionately higher conduction loss out of the diode and instead add them to the conduction loss of the low resistance MOSFET, and thus realize a net increase in efficiency. Getting back to my original observation, as MOSFET devices continue to improve with lower and lower QGs, a controller is needed that can take advantage of all the benefits, not just the lower switching losses, but also the diode conduction losses. Microchip's MCP19035 was designed with low figure of merit MOSFETs in mind. Specifically, it offers two different dead time options. There's a 12 nanosecond version, which work with the latest low figure of merit MOSFETs, and there's a 20 nanosecond version with adaptive dead time for use with conventional MOSFETs. If you're interested in more information on our MCP19035 family of PWM controllers, please visit the product page at www.microchip.com/MCP19035. Here you'll find the product datasheet, which describes the MCP19035's operation and performance. We also offer an Excel-based design analyzer and associated application note, our AN1452. These tools assist you in designing with the MCP19035. The Excel tool automates the many manual equations needed to help you choose components and understand the transient performance with the frequency domain analysis, as well as estimate the power conversion efficiency. And finally, we offer evaluation boards and printed circuit board design files to help get you up and running quickly. These are all available on microchipdirect.com. Thank you for taking the time to learn more about Microchip's MCP19035 DC-to-DC PWM controller family. For additional information, please review the product page at www.microchip.com/MCP19035 or contact your local Microchip support. Thanks for watching.